Okay, we're on to the last chapter of Statistics Year 1, which is hypothesis testing. And I've written binomial here because later on we will do some correlation hypothesis testing in Year 2, as well as some normal distribution hypothesis testing. So this is Applied Year 1, Chapter 7. Now this video alone is not going to be enough to teach you hypothesis testing. It is purely a recap with a few examples to kind of show you everything that I think, roughly everything that can come up on this. So I'm going to try and explain to you hypothesis testing in a nutshell. So what we do is we start off by assuming that some probability for a binomial distribution is true. But it might not be, but we have to assume that something is true so we can do some calculations. So using this assumption, we then calculate the probability of our observation or something more extreme occurring. So we might have seen something happen in real life, and then we say, okay, let's calculate the probability of that thing happening or that thing being more extreme. I'll explain that with an example. And then with that probability, if that probability is very unlikely, in other words, if it's lower than the significance level, it gets us thinking, maybe our original assumption wasn't true. But if that probability is quite likely, in other words, more than the significance level, then our assumption is probably true. We don't have any evidence to say that that assumption is false. So a few little bits of language with this. We use H0 for the null hypothesis, the thing that we assume to be true. And then H1 is the alternative hypothesis, which is what might be true instead. The significance level is the threshold a probability needs to go below for us to reject the null hypothesis. It's this thing that we were talking about over here. And then a little bit about one-tailed and two-tailed tests. If our alternative hypothesis is a probability being less than something or greater than something, it's just a one-tailed test. If our probability is that it is not the thing that we are assuming it to be, then it is a two-tailed test, and we simply halve the significance level for each tail. So we're going to start off by doing two hypothesis tests with p-value testing, and I'll explain a bit about what the p-value is in just a second. And then in the second half of the video, we will look at some things to do with critical regions. So really the best thing is to just dive in and see if you remember these techniques for how we solve like a hypothesis test. So it says here that Mr. Smith believes that 40% of people in his local village support his policies. Maybe he works on the council or something. He is worried that he is understating his support and so conducts a survey with 20 inhabitants of the village. He finds that 13 of them supported his policies. Test at the 5% significance level whether or not Mr. Smith's belief that 40% support his policies is true. Clearly state your hypotheses and the p-value found. So we always have to write the hypotheses out. So we write H0 and we must do a colon. If you do equals, you will not get that mark. So this is the thing that we're just going to assume to be true. And it's this probability that 40% of the people support him. So we're assuming that 40% of the people support him. And then his alternative belief is that he thinks he is understating his support, meaning that there's a chance that the support level is actually higher than 0.4. He actually thinks that it's higher than 0.4. And so he's going to conduct a survey with 20 inhabitants of the village. Okay, what I'm going to write down, you don't have to write this down, but I always like to do this. I am going to assume that H0 is true. In other words, we are now saying that X has a binomial distribution where he's asking 20 people in the village, and the probability that we've assumed to be true is 0.4. You know, I'm probably going to do a little line before this. I'm going to say, again, you don't need to write this to get the mark. Let X be the number of inhabitants who support his policies. I might change in the PDF and say that Mr. Smith is like a councillor or something, just so the question makes even more sense. Okay, so we're going to say X is the number of inhabitants who support his policies. We're assuming that this is true. So X has this binomial distribution. And now we're going to do this thing. We're going to find that 13 of them supported his policies. Now, we're going to be saying 13 people or more extreme. So we're going to calculate the probability of our observation or something more extreme, because that would also contribute to us considering that the alternative hypothesis is true. So we are going to calculate the probability that X is greater than or equal to 13. You'll notice it also matches this inequality. So if it was less than, we would usually be doing something that was less than. But 13 already feels like quite an overstatement, doesn't it? Because 13 out of 20 is 65% of people that he asked. But we need to know if this is significant or whether this is just sort of general variation that we've got here. Now, if you don't have a graphics calculator, you would calculate the probability of you would do 1 minus the probability that x is less than or equal to 12. But I do have the graphics calculator, so I will save myself a little bit of time when I'm doing this calculation for the cumulative stuff. So I'm saying that it's greater than or equal to 13, and the probability is 0.4, and there are 20 trials, which is 0.02102 blah blah blah, and clearly this is less than 5%. So this is actually making us think something quite important here. This is making us think, okay, that was very unlikely happening. Maybe our assumption wasn't true. So actually, this is not true. This is more likely to be true here. So what I'm just going to do is a conclusion sentence, and that conclusion sentence should always be in the context of the question. So I'm going to say, hence, we have enough evidence to reject H0. You could say we have enough evidence to accept H1, but I often talk about H0 rather than H1. So here we have enough evidence to reject H0. So now we actually need to make the conclusion. Mr. Smith's belief is not true. I don't know. Yeah, Mr. Smith's belief is not true. His support is higher than 40%. And that's because our alternative hypothesis is saying that it's greater than 0.4. And the reason he's worried he's understating his support, because maybe that's something that's really good. He can say in his next council meeting, you know, I used to think it was 40% of people supporting me. I actually think I'm understating that. It's even higher than that. Maybe it's going to give him a slightly stronger position in the politics of a village council. Okay, so next one says, a company claims that 8% of its packs of collector's cards contain a shiny. Jack wants to investigate this claim and believes that the proportion of packs containing a shiny is different to 8%. He buys 50 packs and only one of them contained a shiny. Test at the 10% significance level whether the company's claim is supported or not. Clearly state your hypotheses and the p-value found that we have here. Well, I've realized I didn't state what the p-value was in this previous one. I didn't state the p-value. So the p-value in this case is this thing. So I'm just going to say that we have here, that is the p-value. Okay, it's just literally the probability of the thing that we have observed. So let's come back to this one. The null hypothesis is that the probability is as the company claims, which is 0.08, and the alternative hypothesis is that the probability is not 0.08. Jack doesn't think that it's higher or lower, even though he's only got one of them with a shiny, which probably makes us think it's lower than 8%. His belief is that it is just not 8%. So as soon as we've got this, we are moving into a two-tailed test that we have here. So I'm going to say let X be the number of packs with shinies. And we're going to assume that H0 is true, because otherwise how could we do any maths? Assume H0 is true. So X has now got a binomial distribution. He's buying 50 packs, and the probability would be 0.08. And we're going to say that he has only got one pack with a shiny. So it's going to be one or more extreme. That means it's going to be less than or equal to 1, because obviously 1 feels quite extreme. 8% of 50, well, it's going to be 4 packs. So 1 feels very, very low. So we will do 1 or even lower, which is going to be 0. So on my calculator, I am going to be doing the number of trials is 50, probability is 0.08, and it's less than or equal to 1. And I get 0.0827 like this. That is my p-value that we have here. However, that is the p-value. This is a 10% significance level. So because it's a two-tailed test, it will be 5% in each tail, each end of the test. It's two-tailed because you'll have like less than or greater than. We're only looking at the less than end that we have here. So this is actually greater than 0.05. Now, it looked like it was less than the significance level, but we have to remember we have to half the significance level for a two-tailed test. So because 0.0827 is greater than 0.05, we do not have enough evidence to reject H naught. The company's claim is actually supported. So I'm going to say we do not have enough evidence to reject H naught. The company's claim is supported. 8% contain shinies. I'm going to say 8% of packs. I'm going to be really fussy. 8% of packs contain a shiny. So kind of surprising outcome, because 1 out of 50 feels incredibly low, but because of this random variation, unfortunately, Jack got 50 packs and he just got incredibly lucky, okay? 1 out of 50, 1 or 0 out of 50 is 8%, which is more than the significance level. So although it's very, very unlucky, it doesn't actually give us enough evidence to reject the company's claim that we've got there. Okay, then the other approach that we have to hypothesis testing is not using these p-values. I should probably just quickly highlight the stuff with p-values, so that's really clear what we mean by the p-value. The other thing is to do is to do critical regions. Now, for critical regions that we have, what you do is you use the tables, or using the tables, you find the regions where the null hypothesis would be rejected. In other words, where the probability would dip below the significance level. Now, for the upper region, I'm going to give you this tip. What you do is you find the first probability that exceeds 1 minus the significance level. So, I don't know, if it was 5%, it would be 1 minus 0.05. So the first one that exceeds 0.95. And then you simply add 1 on to the x value to get the beginning of that upper critical region. Remember, you have to half the significance level for two-tailed tests, and if it ever asks you about the actual significance level, this is the actual probability that an observation falls in the critical region or critical regions. And again, that will become clearer in the questions that we look at. I've provided these because we'll be using this one for the first question and this one for the second question. They're just the probability tables that you get in the formula booklet. So here we've got Tom. Tom believes that he is better at selling cars than his colleague Stephen. On average, Stephen sells to 30% of the customers he meets. To check his belief, Tom plans to monitor the next 25 customer interactions he has, noting how many end in a car sale. Stating your hypotheses clearly and using a 5% significance level, find the critical region for this test. Okay, so we're going to start off by writing down the hypotheses. The null hypothesis is that he is just the same as selling cars as Stephen. So we're just going to say that the probability is 0.3. But Tom's belief is that he is better. So he is going to be selling more than 30% of the cars that he has. Again, you don't need to write these bits, but I like to do it. Let x be the number of cars sold. And we're going to assume that H0 is true because, we can't assume that H1 is true. How can we do calculations with an inequality sign like this? So assume H0 is true. In other words, X has a binomial distribution where there are 25 customer interactions and the probability is 0.3. Now we have to try and find out how many cars he would need to sell in order for us to reject the null hypothesis. So what we're really trying to do is we are saying the probability that x is greater than or equal to some value has got to be less than 0.05 because that is the significance level. And the aim here is we want to find what A is. So I'm going to use this table that we have down here. Now, we've already got the 25 for the number of customers he's seeing and the probability that we've assumed. If it was the opposite end of the table, we would be looking at the first one that was, the first one as we look up that goes below 5%, which would be this, okay? This would be if we were saying that he was worse at selling than Stephen. If he sold 3 or fewer cars, we would say, actually, you've done a lot worse than Stephen. But we're not doing that. We're doing the opposite end. So I'm going to use this little technique that we've got. For the upper region, we find the first probability that exceeds 1 minus the significance level. So the first one that goes above 0.95, and then we'll add 1 on to the x value. So the first one that goes above 0.95 is this one here, which means our critical region is going to be this section, that x is greater than or equal to 12. And we just think about why that's true. The probability that x is less than or equal to 11 is more than 95%, which means the remaining part, greater than or equal to 12, must be less than 5%. This is more than 95%. This section that's being represented here is representing less than 5%. So I can just either just say straight from the tables, or you could write something down like the probability that x is greater than or equal to 11. I know this is not going to be the right answer. Probability that x is greater than or equal to 11 would be 1 minus 0.9022, or you can just find it from your calculator, which is 0.0978. The probability that x is greater than or equal to 12, we know that that one is going to be our first one that's going to be less than 0.05. That's 1 minus 0.9558. That is 0.0442. That is less than 0.05. Hence, the critical region is x is greater than 12. Hence, the critical region is x is greater than or equal to 12. It's the first one that goes below it. And then part B, it says, it is found that, I've got part B and then part B. Of course, I'm going to change this on the PDF because that is complete nonsense. So part B says find the actual significance level of the test. Well, we could have just written down here the critical region is x over 12, but we've now actually got that the actual significance level is the probability that something appears in the critical region. You can either do it on your calculator, you can read it from the tables. I'm just going to write down that the answer is 0.0442. And then part C of the question, it says, it is found that Tom sold cars to 11 of the 25 customers. Comment on Tom's belief in light of your answer to part A. Well, Tom was probably pretty chuffed, right? Because he sold 11 out of 25 cars, which is 44%. So he was probably like, great, I'm doing really good here. But it seems like it's just random chance, okay? We don't actually need this part here. I'm going to say 11 is not in the critical region. Hence, there is not enough evidence. Not enough evidence to reject H0. Tom's belief isn't supported. He isn't necessarily better at selling than Stephen. He isn't better than Stephen. I'd probably give as much context as possible because I'd hate it in the question to lose the mark for that context part that we've got there. So although it was 44%, what we're saying is there is enough like random variation. He might have just got a bunch of customers who were ready to buy a car. There would need to be stronger evidence. He would need to have sold 12 or more to give us some really strong evidence that he has actually got better at selling cars than his colleague Stephen. Okay, our last one is deliberately without context because I sometimes think if it's without context, it can look a bit scary, but it should be just as easy here. So it says a random variable has distribution B, 12p, binomial with 12 trials and probability p. A single observation is used to test the null hypothesis as p is 0.45 against the alternative hypothesis that p is not 0.45. So immediately we know we have a two-tailed test here. Using a 5% significance level, find the critical region for this test. So it's a two-tailed test, which means the probability will be halved for each tail. And they've told us something in particular here, that the probability in each tail should be as close as possible to 2.5%. If it didn't say that, we would want the probabilities to be below 2.5% because we've halved the significance level in each end. But they've said here they want them to be as close as possible to 2.5%. And then what we'll do afterwards is we will write down the actual significance level of this test. So the as close as possible to 2.5%, we're looking for 0.025 and 0.975 as those parts in the table that we've got here. So I'm just going to write down using the tables. I don't need to necessarily write all of the values. I'm just going to say using the tables. So I think the easiest one for us to find is the one that is closest to 0.025. It is either this one or this one. And I'm going to just do a quick bit of calculating. I'm going to do 0.025 minus this, 0.025 minus this, or 0.421 minus 0.025. So this one, if I just quickly jot it down, is 0.0171 away. And if I do 0.0250083, this one is 0.0167 away to 0.025. So actually the closest one is, have I got the right thing for this? Yes, I have got the right thing. I've got it with 0.045. The closest one is this one, because this is even smaller. Very, very tricky to decide which of those was closest. And then at the other end, we need to decide which is closest between to 0.975. So it's a choice between this one or this one, the blue or the pink. I think it's pretty obvious that it's going to be this one, but if I just check 0.975 minus 0.9644, that one is 0.0106, and then the 0.9921 minus 0.975, that one is 0.0171. Oh, they're both so close. 171. So the closest is this one. Now we've got to be careful for this, because although it's this one, remember that represents 8 or less, so the critical region will be 9 or more. So using the tables, I will write this down, okay? I'm going to say the probability, I probably will do what I said I wasn't going to do. The probability that x is less than 1 is 0.0083. The probability that x is less than 2 is 0.0421. And I'm just going to say this one is closer to 0.025. And then I'm going to say the probability that x is greater than or equal to, so remember this one is 8, it's actually greater than or equal to 9. That is going to be 1 minus 0.9644. That is 0.0356. And the probability that x is greater than 10, that is for the pink one, and that is for the blue one. I'll get all of these sort of highlighted so it makes sense when we look back at the question. Greater than or equal to 10 will be 1 minus 0.9921, which is 0.0079. And actually, I think we decided that this one is closer to 0.025. So the critical region is therefore going to be that x is less than or equal to 1 or x is greater than or equal to 9. So the critical region is x is less than or equal to 1 or x is greater than or equal to 9. So we've got those kind of two extreme ends here. And it wants us to now just write down the actual significance level. So the actual significance level is equal to those two that we're going to highlight the probabilities of. It was the yellow and the blue. So it's the total probability, 0.0356. Let's add those together. 0.0083 plus 0.0356. And we get that the actual significance level is 0.0439. And you don't need to do this last part, but it's worth noting that that is 4.39% that we've got there, which is close to 5%. So the reason that they said that each one should be as close as possible to 2.5% is because although this one is actually higher than 2.5%, overall we do get a significance level that is still around the 5% level. Otherwise we might be pushing it way too low for this particular bit. So a lot of fiddly bits with our calculator here to see which was closest. I need to double check them after this video to make sure I've actually got them closest, and I'll make sure I've changed this as well. You've got to do so much practice on hypothesis testing. Really get your head around this. If you can understand this, hypothesis testing is going to be a lot easier as you go throughout the rest of year 2 stats as well. So I hope to see you in another video, maybe for mechanics.